All right, so we're going to talk about acceleration in this unit. And acceleration, of course, is going to be something that's similar to velocity, but acceleration, there's actually changes taking place in the velocity, whereas constant velocity was the same over a period of time. There are different ways to look at acceleration, lots of different ways to look at it. The idea, as you can see here on the slide, is are you speeding up? Are you slowing down? Are you changing direction? All of these represent acceleration because all of these represent a change in velocity. Acceleration is something you can feel. If you are in a vehicle and that vehicle accelerates, and what do we mean by that? Speeds up, slows down, changes direction. Your body can feel that taking place. It cannot interpret, your body, cannot interpret constant velocity. If you were in a car and the car's windows were completely blacked out and you were on the smoothest road ever created, you could not tell that that car was moving or that car was stationary. You have no frame of reference to know. And it's not accelerating. It's not speeding up. It's not slowing down. It's not turning. It's not changing direction. You actually could not tell that that object was moving. This is how a lot of amusement park rides work, like specifically at Disney World or at Epcot. Things like Mission Space. You get in the spaceship and they make your body perceive that it's doing all these things because your body doesn't know any better. But what they're doing is they're just accelerating a vehicle, spinning it, turning it, making your body feel like it's moving very fast or slowing down or doing whatever. So acceleration is something that it's actually more fun to study because it's something there's a change taking place. It's not just something boring like constant velocity. It is a vector quantity, just like velocity was. So acceleration has magnitude and it has direction. Most of the time you'll see a positive and negative sign used for conveying direction change, but it doesn't mean you can't use west or east or north south or up down left right. You can use different expressions for direction, but acceleration, again, we know it's a change in speed or a change in direction. It doesn't have to be both. It can be just a change in speed or it can be just a change in direction. Either way, you are accelerating. Velocity and acceleration vectors. A vector is, of course, just an arrow, and the arrow can be pointing in various directions, and it can be of different lengths. The lengths represent the magnitude, and the arrow points in a certain direction. So let's look at how they're related. It says if an object's velocity is increasing, we could also say the object's speeding up. The acceleration is in the same direction as the object's velocity. So when you look at these two arrows, you see this arrow here is pointing to the right. You see this arrow here is pointing to the right. They're both pointing the same way. If the velocity vector and the acceleration vector are pointing in the same direction, that object is automatically speeding up. You know that for a fact. You're at a stop sign. You look both ways before you cross. You hit the accelerator, you are now accelerating forward and your velocity is increasing forward. But let's say you approach a stop sign. Your velocity is decreasing because you're slowing down. Your acceleration is always going to be opposite the direction of your velocity. So the acceleration vector, as you can see, points to the left here. The velocity vector is pointing to the right. If these vectors are pointing in opposite directions, that object is slowing down. So you come to a stop sign, you put on the brakes, you're still moving, your velocity is still going towards the stop sign, but the acceleration vector is pointing in the opposite way. So you are accelerating to the left while your velocity is moving to the right. In the upper example, when you're speeding up, your velocity is getting faster, it's increasing, and your acceleration is in the same direction. This is a concept that we will use throughout the semester. And it's a concept that every first-year physics student should know. Velocity and acceleration, same direction, increasing speed. Velocity and acceleration, opposite direction, decreasing its speed, slowing down. So let's take a look at these questions here. A passenger train is traveling on a straight track with a negative velocity and a positive acceleration. Is its velocity increasing or decreasing? Well, let's think about it. If I drew a vector to represent negative velocity, I might draw a vector pointing to the left and just label it velocity. Now again, the left means negative in this case, okay? The positive acceleration vector, I would point to the right, and I'd label that acceleration. Are they pointing opposite directions? They are. In that case, the velocity of this train, of this passenger train, must be decreasing because the two vectors are pointing in opposite directions. The fact that it's a negative velocity, it could have been positive velocity and negative acceleration. In that case, the answer would have been the same. It would have been slowing down, just going in a different direction. The velocity going in a different direction. Kyle is riding his bike and slows down as he approaches hikers on a trail. Explain how his acceleration can be positive even though his speed is decreasing. Well, again, if I drew an arrow to the right, there's positive acceleration. Boom. If he's slowing down, which way does the velocity vector have to point? Well, it's got to point opposite the acceleration, so it'd have to point that way, to the left. Okay, so this is a situation where we have positive acceleration, negative velocity, he's slowing down. If it had been negative acceleration, he would have been traveling in a positive velocity, a positive direction, but he still would have been slowing down. Here we see the formula for acceleration. Now, again, I have a situation with the software taking away my subscripts for some reason. So the value here, A, average, looks like it's an average. No, that should say acceleration, and average should be the subscript. So that means average acceleration is equal to delta V. We already know delta means change in. Change in what? What does V stand for? Change in velocity. Over what? Change in velocity over time. So this T really should kind of be shifted over this way. What's another way to write change in velocity? Well, we could write VF, and again, this should be V sub F, and V sub I over T. So there's our standard formula for average acceleration. If I know the final velocity, if I know the initial velocity, and I know the time that this change took place, and the time that it takes place, I can solve for the average acceleration for that object. Again, this T should be shifted over a little bit, and the VF and the VI should be subscripts. All right, we have a little problem here. We have a fancy sports car, and we see over a span of a few seconds, 0 seconds to 1 second to 2 seconds to 3 seconds, we see that the velocity of this car is going through a change. So we know that it is accelerating. And what you're expected to do here is you're supposed to figure out what would go in the question mark. Well, if you look closely, you can easily see a pattern. I think that's pretty easy to pick up here. We start here with 0 miles per hour. Then after 1 second, we're going 15. After another second, we're going 30. Well, it looks to me like it increased by 15 in that 1 second. So what should the velocity be after 3 seconds? Well, if he's increasing by 15 every second, and he's at 30 miles per hour at 2 seconds, how fast is he going to be moving at 3 seconds? Well, you would just add the 15 to the 30, and you get 45 miles per hour east. And of course, we have to put the east there because we're dealing with a vector quantity, acceleration, not a scalar quantity. So how quickly is the velocity increasing? Well, it's increasing 15 miles per hour per second. That's not a very common unit for acceleration in physics, but it is something that you might see on a car commercial for a real fast car, sports car or whatever. But every second, we're increasing by 15 miles per hour. That is the definition of acceleration. It's the change in velocity over a specific period of time. In this case, our time is every second. So when we're trying to address the unit for acceleration, if you think of the formula, it's going to have change in velocity, and that's going to be in meters per second, over time. And time is usually in seconds. So if we take this and we expand it out, it would look something like that. We'd have a meter per second times 1 over a second. And of course, a second times a second is a second squared, and that would give us a meters per second squared. Very important that you remember to put the squared value at the top of the seconds. If you just write meters per second, that's just a unit for velocity. You could also write meters per second. That would be okay as well. But usually we just write meters per second squared, and that's the standard unit for the acceleration measurement in physics. All right, so this is a chart that when you are given it, let's say with some of the information missing, you should easily be able to fill it all in. So let's look at the first row. It says that this object is speeding up, and it looks like the velocity is positive and the acceleration is positive. We see they are both in the same direction, and if that's the case, that automatically means the object is speeding up. Should be no mistaking that. Well, the same thing happens on the second one. In the second problem, or the second row, the motion is speeding up. And again, you see the signs are negative. They're both negative. Velocity initial is in the negative direction. Acceleration is in the negative direction. So if they're both in the same direction, again, the object's speeding up. Don't let the negative sign confuse you into thinking that it's slowing down. And the third row has an object slowing down, and we notice that the initial velocity is in a positive direction, and we notice that the acceleration is in the negative direction. So this would be you coming to a stop sign. You may be traveling in a positive direction, but you're slowing down, so your acceleration is opposite your movement. So if your movement is positive, then your acceleration has to be in the other direction. So that's why it's a negative sign. And the same thing comes up on the fourth row, where you have a negative initial velocity and a positive acceleration. Well, again, they're opposite signs, so that means the object must be slowing down. The example that I used in row 3 could be the same example in row 4. You're coming to a stop sign, but in this case, you're traveling in a negative direction. So you're coming to the stop sign, you're still slowing down. So you're traveling in a negative direction, your acceleration has to be in the opposite direction. The fifth row says the object is traveling at constant velocity. Well, we see acceleration, there is no acceleration. It's all traveling at a constant velocity. And if that's the case, then the object's not speeding up or slowing down, which means that the initial velocity could be either direction, positive or negative. But once it gets going, if its acceleration is 0, then no change in velocity is taking place, and we call that constant velocity. The sixth row, speeding up from rest, well, common sense hopefully would tell you that something speeding up from rest is going to be of initial velocity of 0, no doubt. And if it's speeding up, we know it's accelerating. Well, we don't know the direction, but we know that it could be one of two things, positive or negative. So it's going to be speeding up either way, whether it's moving in a negative direction or positive direction. And then, of course, the last one, probably the easiest one of all of them, remaining at rest, no initial velocity, no acceleration. And certainly you should realize that that means no movement at all. All right, so we're going to try out some practice problems here. And one of the things that you need to follow in physics is organization patterns. You need to make sure you stay organized when you're doing any word problem, so you keep all your variables straight. So I would like for you to adopt the same sort of method that I use in my example problems. First thing you should do is write everything that you're given. Write what you're trying to find, look for the formula, rearrange the formula, plug in your numbers, solve for your unknown. That's what you should try and do each time. So let's take a look at number 1. A brakeman on a bobsled team slows the sled from positive 12 meters per second. Positive 12 would have to be our initial velocity. To rest. Now, what does to rest mean? Well, it means it's stopping. So if it's resting, then its velocity, final, has to be 0. In 4.5 seconds. Well, t must be 4.5. Calculate the average acceleration of the bobsled team. And typically we write average acceleration values in meters per second squared. So I go to my formula sheet and I look up a formula for acceleration. And when you do that, you see that average acceleration equals Vf minus Vi over delta t. Vf minus Vi over delta t. Final velocity minus initial velocity over delta t. Well, we're solving for the average acceleration, which means we don't need to do any rearrangement, thankfully. So we just plug in our numbers. Vf is 0 minus Vi, which is 12 meters per second, over 4.5 seconds. We end up with 2.6 repeating. And we would round to 2 sig figs. Our unit would be meters per second squared. And there's one more thing that's missing. What does 0 minus 12 give you? A negative number. So this is a negative answer. The reason it's negative is because this object is slowing down. What is its velocity direction? Its velocity direction, if you look up here, is positive. So for that to happen, the object must have opposite signs for velocity and for acceleration. But notice that the math did the work for you. It gave you a negative answer, so that helps you out. 2.7 or negative 2.7 meters per second squared. Number 2, a Vespa accelerates from positive 21 meters per second. So that would be initial velocity. To positive 27 meters per second. So that's final velocity. With an average acceleration of positive 2.9 meters per second squared. Again, that's a little typo there. That should be an exponent. How long does it take for this acceleration to occur? Well, that looks like we're solving for t. And typically we have our t values in seconds. Well, I take a look at my formula for acceleration. I know it's Vf minus Vi over t. And I'm solving for t. And if I rearrange this to solve for t equals Vf minus Vi over a. Essentially, the a and the t switch places. If you're not sure algebraically what we did here, we multiplied by t, and then we divided by a. And that's how we got here. All right, so we're ready to plug and chug. Plug and chug our answer out. Vf, well, we go to look at my given values. Vf was 27 meters per second. Minus Vi, Vi was 21 meters per second, over 2.9 meters per second squared. And we end up with, we want to do 27 minus 21, we know that's 6. And then 6 divided by 2.9 meters per second squared. T equals, and I'm going to write the unrounded answer here, 2.808965552 seconds. And of course, we would round to 2 sig figs there, and that's 2.1 seconds. We don't need any sign on there. Time is always going to be positive. 2.1 seconds is our answer. And if you're not sure how that seconds ends up there, if you take away all these numbers and just do the units, meters per second over a meters per second squared gives you a second. All right, number 3, Gina's golf cart accelerates at negative 4 meters per second squared. Again, that right there should be an exponent. That looks like an acceleration value. So I'm going to say acceleration is negative 1.4 meters per second squared. From positive 7 meters per second. So it's traveling initially at positive 7 meters per second. And it comes to a complete stop, which means that Vf must be 0. How long does it take the golf cart to come to a complete stop? And we know we're going to have that in seconds. So I go to my trusty average acceleration formula. And I realize, again, I'm going to solve for t. So quick rearrangement. T is equal to Vf minus Vi over t, over a, excuse me. And now we're going to plug in our numbers to get our answer. We're going to have 0 for our Vf, because it comes to a stop, minus a negative 1.4 meter. Check that. Not paying attention to my numbers here. Vi is 7, so that would be 7 meters per second, over negative 1.4 meters per second squared. So we're going to have negative 7 divided by negative 1.4. And when we do that, we end up with 5 seconds for our answer. 5 seconds. Now, obviously, time is going to be positive always. But you'll notice that the negative on the top and the negative on the bottom canceled it out and gave us a positive answer. So the math worked out for us. If you had ended up with a negative 5 seconds in your answer, you might want to go back and look at your numbers and see if you forgot a sign somewhere. All right, Number 4, an aircraft accelerates from positive 10 meters per second. So that looks like a VI, positive 10.0 meters per second, at an acceleration of positive 16 meters per second squared. That's a pretty big acceleration. Again, that should be squared. For 12 seconds. What is the aircraft's final velocity? What is the aircraft's final velocity? So we're trying to find velocity, and we know we're trying to find final velocity, and we know that that's going to be in meters per second. So I go to my formula for average acceleration. It's VF minus VI over T. This one is a little bit more complicated as far as rearrangement goes. You would want to first off get rid of T. So you multiply both sides by T. And then after you multiply both sides by T, you want to get rid of VI. Well, it's being subtracted, so you would add it. So you would end up with something that looked like this. VF equals AT plus VI when you rearranged it. Again, multiply by T and then add VI to both sides. That's where you would end up with. So acceleration rate is 16 meters per second squared. T is 12 seconds. Plus VI. VI is 10 meters per second. And VF ends up being positive 202 meters per second, which, in case you're wondering, is 452 miles per hour. I went ahead and converted that. You don't have to convert that on this one, but I was just curious how fast that was. So that would be our answer, 202 meters per second. And the idea here, of course, the reason the positive is on there is because velocity needs a direction. So the positive is in front of the 202. And we know that this object's speeding up because the velocity is in a positive direction and the acceleration is in a positive direction. And we've just learned that when an object's speeding up, that those two variables are in the same direction always. All right, another problem here. During takeoff, a Boeing 737 accelerates from rest at 1.1 meters per second squared. So let's say we have meters per second squared, so you should identify that as an acceleration value. So that's 1.1 meters per second squared, that's positive, for 0.9 minutes. T would be 0.9 minutes. I'm going to go ahead and do something here because I know I'm going to need to do it later. I'm dealing with seconds quite a bit in these problems, and this is given minutes. So I'm going to go ahead and I'm going to convert this to seconds real fast. And there's 60 seconds in 1 minute. So I'm going to essentially just multiply by 60. And I get 54 seconds. I think that'll be much easier for the rest of this problem. And it accelerates from rest. Well, from rest means the initial velocity must be 0. And the question wants us to figure out what will its final speed be at the end of this time interval. So we're solving for VF. And it's going to be in meters per second. All right, we take a look at our formula for acceleration, VF minus VI over T. We want to rearrange and find VF. And I think we did this on the previous problem. We ended up multiplying both sides by T and then adding VI to both sides. And that gives us AT plus VI. And now we're ready to plug in our values. So acceleration is 1.1 meters per second squared. T is 54 seconds. Remember, we made that change earlier to make this easier for us. VI is 0, so that's a piece of cake. We don't even have to worry about it, really. And we're just multiplying 1.1 times 54 seconds. And I get 59.4 meters per second. And of course, we need a direction on that. Well, it's speeding up. We know its acceleration was positive, so we know that its velocity is going to be positive. And again, if you're curious, I converted that to miles per hour. That's 133 miles per hour, just for my curiosity. And there you go. All right, so these are called the kinematic equations. Sometimes you can call them the UAM equations, which stands for uniformly accelerated motion. But these are 4 equations that are good friends to physics students, because these allow algebra-based physics students to solve for many unknowns in situations where the acceleration is constant. And that is a key here. You can only use these formulas when the acceleration rate is staying the same throughout. So if you have a situation where the acceleration is changing, if you have a changing acceleration throughout a process, you cannot use these. That's where you get into a little bit higher math, some calculus, things like that. And in this course, we don't get into that. So these are the 4 formulas that we'll use. And our acceleration values are always going to be constant, so we don't have to worry about the changing acceleration. And these values, there's essentially 5 variables that you have to deal with, and we'll talk about those in a moment. They're derived from, you can derive them from graphs, you can derive them from basic algebra substitution methods. You do not have to derive these. You will have these on your formula sheet and be able to access them to solve any problem in kinematics or UAM physics. So let's start talking about these formulas. So we can discuss this idea of what UAM means. It says an object has uniformly accelerated motion. It is changing its velocity at a constant rate. That's what we mean by uniformly accelerated motion. The acceleration is changing at a constant rate. So, or the acceleration is constant and the velocity is changing at a constant rate, excuse me. So if something has an acceleration rate of 2 meters per second squared, that 2 meters per second squared acceleration rate is going to stay the same throughout the motion of the object. Objects falling from the sky, their rate is 9.81 meters per second squared. That rate does not change as the object is falling. The velocity does, but the rate of acceleration does not. A ball rolling down a driveway, a bomb falling from a plane, not the best example, but it's still good for this course. A bicycle in which you have applied the brakes consistently. Now, we say applied the brakes, but we need to make sure you understand you can't change the amount of squeezing on the brakes as you're going through the process of stopping the bike. That needs to be consistent. Or a rock thrown up in the air. We know that a rock, as it goes up in the air, it slows down. Well, it slows down at the same rate that it speeds up coming down. So that's because the acceleration rate stays the same. And in algebra-based physics, we have to think ideally. We ignore wind. We ignore the smoothness of a surface because that does have an effect. We ignore how consistent you brake the bike. We always say the acceleration rate is always the same. It does not change. And that's very important for this course. If you start changing acceleration rates, you're going to deal with something higher than algebra. Okay? So don't overthink it. Don't overthink it. All right, so we said there's 5 different variables that you have to deal with. VF, and again, that should be V sub F. VI, acceleration, change in time, change in x. Change in x, delta x, means displacement. We know that means change in position. Time change, delta t. Acceleration is just an a. VI, the initial velocity. VF is final velocity. And typically we'll use the base units, the SI units or metric units for each variable. VF and VI, those would be meters per second. Acceleration rate would be meters per second squared. Change in time, typically we use seconds. And delta X, typically you see that in meters. It doesn't mean that we'll not throw around the units every once in a while, change them up, but most of the time we stick with the metric units. Here's the beauty of kinematics. Here's the beauty of UAM math. If you know 3 of these 5 variables, any 3, you can solve for the other 2 unknowns. So that is going to be a key problem for you every time you're doing a UAM problem. What are the 3 variables and how can I find the other 2? So if you know VF and you know VI and you know A, using the kinematic equations, you can find delta T and you can find delta X. Any 3 combinations, you can find the other 2. There is no exception to that rule. This is why it is so important for you to write down all of your givens when you are reading a word problem and write down what it is you're solving for. That is how to do good physics. Bad physics is just starting to solve the problem randomly without writing anything down, just trying to plug in numbers before we even think about it. So try and follow that pattern of writing down your knowns, your givens, and then your unknown, and then figuring out which formula to use. Very, very important. All right, so this is the first true kinematic or UAM problem that you're going to come across. And I've written the kinematic equations, the UAM equations right there, just so we can choose from the 4 that I gave you. Let's go through it. Mr. Martin is riding his bike at plus 6.36 meters per second in a straight line when he applies the brakes at a constant acceleration. Now that term, constant acceleration, is important because it allows you to use these formulas. When you see constant acceleration, that's a trigger for you to realize, oh, I can use my kinematics. But most of the time, it doesn't have to be written in the problem. You can just assume that it is constant acceleration. But for this problem, I put it in there. He's riding his bike at 6.36 meters per second. That looks like an initial velocity. So I'm going to put initial velocity positive 6.36 meters per second. When he applies the brakes at a constant acceleration, so I'm slowing down. After 1.01 seconds, that looks like a time, he has traveled plus 4 meters. Now that is a displacement. And they are asking us to find, first off, what was his acceleration in meters per second squared? Remember that squared should be a little bit higher exponent. And what was his final speed? And that would be in meters per second. So let's take a look. I told you earlier in the video that as long as we knew 3 out of the 5 variables, we could solve for the other 2. And sure enough, we know 3 out of the 5, which means we can solve for acceleration, which is going to be meters per second squared, and we can solve for VF, which is going to be in meters per second. So where do we start? Well, it doesn't really matter. Let's just go with A and start from there. The problem with this is you have to figure out which formula to use. And sometimes that can be confusing to students. But if you think about it this way, look for the variables that you have in the formula and look for the variables that you're trying to find. If one of the variables that you don't know and you're not trying to find is in the formula, then don't use it. So let's just say we were going to go ahead and start with A. We're going to solve for acceleration. I look over here and I notice that this formula doesn't have A in it, so I can't use that one. This formula has A in it, so that might be some potential right there. The third formula has VF in it and A. Well, I don't know VF, and I don't know A, so there's no way I could use this one. And then the last problem has A in it, and it has VF in it. Again, I don't know either one of those, so there's no way I can use that formula, which narrows it down to the second one. So the second one says delta x equals VIT plus 1/2 AT squared. Now I'm trying to find acceleration, so what I need to do is rearrange this to solve for A. Well, the first thing I would do is I think I would subtract the VIT. So I'd end up with delta x minus VIT equals 1/2 AT squared. Then after I subtract the VIT, I want to get rid of that fraction. So I'm going to multiply both sides by 2. 2's cancel. I'm going to multiply this side by 2. I get 2 delta x minus 2 VIT equals AT squared. And then how am I going to get rid of the t squared? Well, I'm going to divide both sides by t squared. And when I do that, I end up with A equals 2 delta x minus 2 VIT over t squared. So I've solved for A, and all the variables that I need on the right side are listed over here on the left side of the screen. So I can just start plugging in my values. 2 delta x, well, that's 2 times 4.00 meters minus 2 times VIT. Well, VI is 6.36 meters per second, and T is 1.01 seconds, 1.01 seconds. Now, of course, that's going to cause my seconds to cancel, right? Actually, that is not right. Excuse me. My seconds aren't going to cancel because I need them in the answer, seconds squared. But eventually, we'll see that meters per second squared comes up. So sorry about that there. And all of this on the top is going to be over. It's going to be over t squared, and t is 1.01, so 1.01 squared. So we extend it out. We say, okay, 8.00, that's our 2 times 4, minus 2 times 6.36 times 1.01, that is 12.8472 over 1.01 squared, and that's 1.0201, 1.0201. And that will give us negative 4.8472 over 1.0201. And we divide 4.8472 by 1.0201, and we end up with negative 4.75, and we know acceleration is meters per second squared. I left out the units. In this area here and here because it was getting a little crowded. I don't recommend doing that, but I was just trying to save some space, so that's why the units were left out. But those all would end up with with meters per second squared. Now, does the answer make sense? Well, I was slowing down on my bike, and I had a positive velocity. Did I come up with a negative acceleration? Sure enough, I did. And because of that, the answer does make sense, negative 4.75 meters per second squared. All right, so now we found the acceleration, and so we're ready to solve for the VF. Now with VF, we have some more convenient options. If you think about it, when we first started the problem, we only had 3 of the variables, but now we have multiple variables. We have 4 variables, and we're only asked to solve for the fifth one, and the fifth one being VF. So I can use the other formulas if I want, as long as they have what I'm looking for, in this case VF, and they have the other variables that are given in the problem. So now we have a situation where we want to solve for VF, which was our other unknown. And we really could use any of the formulas that we wanted to. I traditionally will use the formula that is the easiest to deal with if I can, and that's going to be this one here, the third one listed. If you're not very confident in your acceleration answer, if you're not sure your answer to A is correct, then you would be stuck using the top one, because that has VF in it and then all the given variables, T, VI, and delta X. So if you didn't feel comfortable with your answer for A, you might have to go back and use the first one. But I'm going to use the second one. And the second one is VF, the third one, VF equals VI plus AT. And the nice thing about this one is, yeah, there is no rearrangement necessary. It's already solved for VF. So VI is 6.36. I'm going to leave off the units just to save some space here. The acceleration is negative 4.75, but we probably, because of sig fig rules, should not write that out rounded. 169,101. And that's times the t, which is 1.01. Now again, this part here, the reason I did not write the rounded answer is because when you put the answer that you used from another problem into a second problem, you don't want to put in the rounded answer. You want to put in the unrounded answer, because then you're essentially rounding twice. You know, if you round twice, you end up being farther away from the answer. So we get 6.36, and that'll be minus whatever that long decimal number is times 4.01. It's 4.799, 20792. And when we subtract 6.36 minus 4.799, 20792, we end up with a VF of positive, and I need that positive in there because I have to make it a vector quantity. It's got a velocity, meters per second. And does the answer make sense? Always go back and look. 1.56 meters per second, well, what was I going at the beginning? I was going 6.36, and I was slowing down, so it should be less than what I started at. And there's your 1.56 meters per second. So hopefully that takes you through your first uniformly accelerated motion problem, or UAM problem, and sometimes we call them kinematic problems. But this is why you should stay organized. Stay organized, write out all your given values, write what you're solving for, and figure out what formula to use. Once you use the formula, you plug in your numbers, and you solve your unknown. Whether you prefer to plug in your numbers first and then rearrange, or if you want to rearrange with the letters, then plug your numbers in, That's what I prefer to do. That's what we did on this problem. It's up to you. I think solving for the variable with just the letters and not plugging any numbers in, I think that's easier to rearrange first, then plug the numbers in. But it's up to you how you want to do it. All right. All right, so we have a basketball, rolling down an incline, starting from rest, and it's going to accelerate down the hill at 2 meters per second squared. So let's talk about what that means. Now, of course, we would write 2 meters per second squared. That's the same thing as 2 meters per second every second. So if it's starting up here, rolling down the hill, then every 2 meters, or every second, it's going to be increasing its velocity by 2 meters. That's what 2 meters per second squared means. Every second, it's going to increase its speed, or velocity, by 2 meters. So the question, first question, says if the initial velocity is 0, what would the velocity be after 1 second? Well, this should be common sense to you, but let's talk about it. If every second it's increasing by 2 meters per second, and it's starting at 0, after 1 second, how fast is it going to be going? Well, it's going to be going 2 meters per second, because every second it's increasing by 2 meters per second. It starts at 0. It increases its speed to 2 meters per second. And how would that change after 2 seconds? Well, again, every second it's adding 2 more meters per second. So if after 1 second it was going 2 meters per second, then after 2 seconds you'd add another 2 and you get 4 meters per second. And then of course we could extend this out for 3, 4, and 5, and we're just adding 2 meters per second for every answer. So after 3 seconds, it would be 4 plus 2, and that would give us 6. After 4 seconds, it would be 6 plus 2, and that would give us 8. And after 5 seconds, it would be 8 plus 2, and that would give us 10 meters per second after 5 seconds. Right, the last question says to use delta x equals VIT plus 1/2 AT squared and solve for x for the rest of the table. Now I've blocked out that column so that we could do this without looking at the answer. And again, let's remember delta x, displacement, VI is initial velocity, t is time, and that's plus 1/2 acceleration times t squared. So what do we have going here? Well, let's just take the answer after 1 second. So we know that the time is 1 second. We're trying to find delta x, that's our unknown. What would be our initial velocity? Well, our initial velocity is 0. Remember, it started at 0, so VI is 0. And do we know the acceleration rate? We sure do. Acceleration rate is 2 meters per second squared. So by rule, remember our rule, do we know 1, 2, 3 of the 5 variables? We do. So we can use this formula to solve for for delta x. Now, what's nice about this is if you look at this part of the equation right here, what is VI for every second for 1, 2, 3, 4, and 5? Well, VI is 0. And if vi is 0, what can we do with this part of the equation? We can cross it out. We don't need it. So it becomes delta x equals 1/2 at squared. And again, the reason it goes away is because if vi is 0, it doesn't matter what t is, it's going to get canceled out anyway. And then let's take a look at the acceleration rate. We have 1/2 2 times t squared. Well, we're taking 1/2 of 2. 1/2 of 2 is 1. And then we're squaring 1. So delta x equals 1 meter. So our change in position, our delta x, is going to be, after 1 second, 1 meter. And notice something here. For the rest of the rows, for 2 seconds, for 3 seconds, for 4 seconds, for 5 seconds, everything's staying the same except for time. We're increasing time by 1 second each row. vi is still going to be 0, and a is still going to be 2 meters per second squared. So really, if you think about it, this part of the equation, this part right here, will reduce to what every single time? Well, it's going to be 1/2 of 2 every single time. So really, all we have to do is square the time, and that will give us the answer. Let me show you what I mean. Let's go ahead and clean this up a little bit here. So let's say we were doing 2 seconds. So that means this is going to be 2 seconds. 2 seconds. We would have delta x equals 1/2 of 2, right? A is still 2 meters per second squared, times 2 squared. So we see this 2 squared is really going to give us the answer. And delta x equals 4 meters. So this is going to be positive 4 meters. Okay. So we really don't need to do what's in parentheses here each time. We can just say, t squared, get my answer just squaring t. So let's think about what the answer would be for 3 seconds. Well, for 3 seconds, you're going to have 3 squared. And 3 squared is 9 meters. And 4 squared is 16 meters. And 5 squared is 25 meters. So I think you can see that as time goes by, it's not the acceleration that speeds up, it's the velocity. And the velocity is getting faster, so it's going to cover more distance in less time. And that's why those numbers increase over time. All right, so now we are going to do a similar problem, but in this case, we are going to be rolling the ball up the hill. We're rolling it up the hill, and it says we're starting from the 25 meter mark. So that is our initial position. It's 25 meters. And we're going to be rolling the ball up the hill at an acceleration rate of 2 meters per second squared. If the initial velocity is negative 10 meters per second squared, so VI is negative 10, what would the velocity be after 1 second? Well, now remember, this is going uphill. So you should be able to reason that if something's going uphill, it's going to be slowing down. And you can tell that again because the velocity is negative and the acceleration is positive. They are opposite signs. They are opposite in their vector direction, which means the object's got to be slowing down. And it's slowing down every second by 2 meters. So if we start it at negative 10, then it's going to drop by 2 meters per second after the first second. Well, negative 10 plus 2 meters is negative 8. So after 1 second, it's going negative 8 meters. And it continues to slow down, and after a second part, after the second second, it goes down another 2 meters per second. So it goes from negative 8 to negative 6. And then after 3 seconds, it drops to negative 4. And after 4 seconds, it drops to negative 2. And after 5 seconds, it has come to a complete stop, 0 meters per second. All right, so the last question asks us to use this formula again. We just used it in the previous problem, and solve for x for the rest of the table. Now, be careful on this one, because the previous problem, the ball was starting at point 0 and was heading down the incline. Well, on this one, the ball is starting at 25 and is heading up the hill. So we have to be careful when we say, when it says to find x, it's asking you to find where it is after each second, not how far it's gone. So notice the way that this is written. If it was wanting you to find delta x, then that would just be finding the change in position. But because this data table is saying to find x, that means that we have to solve for final position, not delta x, not the change in position. So let's take the first part here. Let's go ahead and get rid of the drawing. And after 1 second, we'll say t is 1 second. And we know its acceleration rate is 2 meters per second squared. And we also know that it is traveling at negative 10 meters per second. So that is its VI. And we want to find x. And really we want to find xf. And remember, delta x equals xf minus xi. So if you write this question out, we have delta x, we have delta x equals VIT plus 1/2 AT squared. And remember, delta x can be written xf minus xi, and that equals VIT plus 1/2 AT squared. All right. So what is xi? Where is it initially starting from? Remember, we said that xi was 25 because it's starting from that 25 meter mark. We know VI is negative 10. We know t, because we're just doing the first second, is 1. And we know a is 2. And we know t is 1, and that's squared. So we have xf equals 25. I'm rearranging here. I'm adding the 25 to the other side. 25 plus 10 times 1 plus 1/2, 2, 1 squared. And we're going to take this to the next page here. I'm going to add at the first answer, you see it says 16. Again, that's the value 16 is where it is after that 1 second. So it's moving up, and if you're wondering what the displacement would have been, it's going to be from 25 to 16. Well, that's 9 meters. So if you solved for delta x, you would have gotten 9 for your answer. But since the top of this data table asks us to find x, then we have to follow those rules. Data table, we see 9 meters is where it's located after that second passes. Now again, we're not solving for delta x here. Delta x would have been what? Would have been 7 meters, I guess, for the second. It only covered from the 16th meter point to the 9 meter point. But again, we found where it was, what its final position was, 9 meters after 2 seconds. Over here, 4 meters is the location. And what's happening to its speed as it goes up the hill? It's covering less ground. Why is it covering less ground every second? Because it's getting slower. It's getting slower, so we would expect that to happen. Sure enough, 1 meter is our answer for 4 seconds, the last row. So this one can be a little confusing because at the distance from 25 to 16, that's 9 meters, and of course the negative sign is there because we know that it's going in the same direction as the velocity, and you see all the velocities are negative. So negative velocity means that it's traveling in a negative displacement. That for us. And we have, let me just rewrite that one. We have xf equals 25. Remember that came from the other side of the equation. Plus negative 10. That was the VI times change in time, which is 1 second, plus 1/2, 2 times 1 squared. So now we have to take all this and consolidate it down to our answer for xf. So let's take it a little farther. 25, let's see, it'd be minus 10, and 1/2 of 2, that's 1, times 1, and that gives us 1. So 25 minus 10 plus 1, 25 minus 10 is 15, plus 1 is 16 meters. So the final position after 1 second is 16 meters. So if you go back and look, all right, so I'm just going to say follow the same policy for the next second, for the second part. After 2 seconds, xf minus xi is still 25, equals negative 10. Remember, that's the initial velocity. Now we're doing it for the second, so that's 2 seconds, plus 1/2 of 2 times 2 squared. So we have xf minus 25 equals negative 20. This is going to be a 1, and then 2 squared is 4. So we're going to have xf, and negative 20 plus 4, that's negative 16. and we're going to add 25 to that, and negative 16 plus 25 is 9 meters. And if we go back and look at our, all right, so we can try it again for 3 seconds. xf minus xi is still 25, and negative 10. Now we're doing 3 seconds, so times 3, plus 1/2 of 2, times 3 squared. And of course, our xf minus 25 is going to be negative 30. And then 1/2 of 2, that's going to be 1, and 3 squared is 9. So we're going to say negative 30 plus 9, that would be what, negative 21. And negative 21 plus 25, because we got to bring that 25 over, is 4 meters. So let's take a look and see what. And then the 4th second, we have xf minus 25 equals negative 10 times 4 this time, right? Because it's 4 seconds. Plus 1/2 of 2 times 4 squared. So we have xf minus 25, negative 40. And then, of course, this is 1 plus 16. And negative 40 plus 16. And that's going to be, what, 24? Negative 24. And negative 24, and we're going to add 25 to the other side. Negative 24 plus 25 is 1 meter. So let's go back and look. And then for 5 seconds, xf minus 25 equals negative 10 times 5 this time, plus 1/2, 2 times 5 squared. So xf minus 25 equals negative 50. And of course this is going to be 1, so 5 squared is 25. And that's going to be plus 25. Negative 50 plus 25 is negative 25. And then we add the 25 from the other side to the 25 that's already there, the negative 25. Negative 25 plus 25 gives us 0 meters. And that is our answer for asking us to find delta x here. They were asking us to find x. They were finding where is that ball located after each second along this 25 meter driveway. And every second we saw it slowing down. We saw it covering less space. The acceleration rate was not changing, but the velocity was getting less and less. Just to give you an idea, what if we had solved for delta x after the first second? Let's say what we were going to solve for delta x. So we would have done vi, which was 10 meters per second, negative 10 meters per second, times t, which is 1, plus 1/2 a, and a is 2 meters per second squared, times 1 squared. And we end up with negative 10 plus, and what does all of this become? It becomes 1/2 of 2, which is 1, and then 1 squared is 1. So what's negative 10 plus 1? That's negative 9 meters. That would be the displacement for the ball. And if you go back and you look, we wrote a negative 9 up here. All right, so we're going to look at a position time graph here. We're going to look at a little bit between instantaneous and average. I think that most of you can look at this and notice it's got a object moving starting at 2 meters and moving to the 7 meter position over a period of time of 15 seconds. And the first question up here asks you, are the VF and the VI variables instantaneous or average velocities? Well, if you think about our formulas and you think about those two variables, VI and VF, those were velocities at specific points in time. They were not velocities over a period of time. So the VF and the VI in our kinematics or our UAM equations are instantaneous. Instantaneous. Forgot how to spell there for a second. Instantaneous velocities. So that would be your answer to the first question over here. And the other question down here at the bottom says, why is the first velocity formula that we learned, and I believe the first velocity formula that we learned was delta x over delta t. Why do we consider that v to be an average velocity? And I think you can see that this average velocity is over a period of time. That delta t means over a change in time. So that's why we say this is average velocity. And then our VI and our VF are instantaneous velocities. All right, so if I asked you guys on this graph to find the velocity for 0 to 5 seconds, am I asking, you can think about this yourself, maybe pause the video, am I asking for an instantaneous velocity, or am I asking for a average velocity? So pause it here, maybe think about it. Well, hopefully you realize that 0 to 5 seconds is over a period of time. So if we were trying to find the velocity from 0 to 5 seconds, we would want to use our formula for average velocity, delta x over delta t. And if you look at the graph, you'll notice that the displacement is 0 and the change in time is 5 seconds. So that's how we calculate over here that the velocity from 0 to 5 seconds is 0. Now you could have figured out that the velocity from 0 to 5 seconds was 0. You can look in the graph and just pick it out, but notice here we have the slope. And the slope from 0 to 5 seconds is a horizontal line, and we know that the velocity of an object on a position time graph is equal to the slope. So you can see that the slope from 0 to 5 seconds is 0, and that would have let you know that the velocity is 0. So we also want to try to figure out the velocity from 5 to 10 seconds. And we know that's going to be xf minus xi over tf minus ti. And xf is the final position, and that would be 7. xi is the initial position, that would be 2. Over tf, well, the final time is 10 seconds. The initial time is 5 seconds. So now we're going to have 5 meters over 5 seconds. And that gives us 1 meter per second. And we can see that down here. Now, again, I'll ask you, is that velocity an instantaneous velocity, or is that an average velocity? Think about that. Hopefully, you see that it is from 5 to 10 seconds. That is a period of time, and therefore, it is an average velocity. So if I was to ask you what the velocity was at 7 seconds, you hopefully could answer that it would have to be 1 meter per second. And the reason for that is, remember that the slope of a distance time graph is equal to the velocity. So the slope of this line is 1 meter per second all along it. And if I was to ask you what the velocity was at 9 seconds, you would get the same answer, 1 meter per second, because that's the slope of the line. Are these velocities, when I say velocity at 7 seconds, and when I say velocity at 9 seconds, are these instantaneous or are they average? Well, again, pause it, think about it. Hopefully you said instantaneous, because now we're talking about specific times, 7 seconds and at 9 seconds. We're not talking about a time period. Okay? Even if I said something like, what's the velocity at 7.392567483 seconds? Even throwing all those decimals in there, it's still an instantaneous velocity, and it would still be 1 meter per second because it's along that same slope. Right there, it's along that same slope. So we notice from that graph that the average velocity from 5 to 10 seconds is also equal to the instantaneous velocity between 5 and 10 seconds. So now let's go through and figure out the average velocity for the whole amount of time, for the whole 15 seconds. So I know the average velocity is going to be equal to xf minus xi over tf minus ti. I know xf, the final position, is 7 meters. I know xi, the initial position, is 2. And the final time is 15 seconds. The initial time is 0. So we're going to have 5 divided by 15. And that's going to give us 0.33 meters per second. You can see that value right down here. So if we wanted to show this velocity on the graph, how would we show that 0.33 meters per second? Well, if you look closely at the graph, I've already done it. This red line, this dotted red line, is the line from the starting position, starting time, till the finishing time. So the slope of this red dotted line here is 0.33 meters per second. So that's how we can show the overall average velocity, with how we can illustrate it with that red dotted line from t equals 0 all the way to t equals 15.